Today we are explaining the paper Rethinking Classifier-Free Guidance and on Policy Diffusion Distillation.
What problem does the paper find in the way diffusion models are distilled?
The paper studies on policy distillation, where a student learns from teacher predictions on states that the student itself visits. The trouble appears when both predictions are combined with classifier-free guidance before they are matched. The combined error can look small even while the two underlying branches disagree.
Before the failure case, what do the positive and negative branches mean?
In classifier-free guidance, the positive branch uses the requested condition, such as a text prompt or control signal. The negative branch uses a weaker or null condition, and the two velocity predictions are combined with the guidance scale gamma.
So what is wrong with matching only that guided velocity?
Let E plus and D minus be the teacher minus student errors in the two branches. Matching the guided prediction only requires gamma times E plus plus 1 minus gamma times E minus to be 0. That is one equation for two unknown error vectors, so infinitely many non-zero pairs can satisfy the loss. The paper names the harmful case negative branch asymmetry, or NBA. It occurs when the teacher's negative branch contains privileged information that the student cannot reproduce, so training reduces the positive error while allowing the negative error to grow.
Does the ambiguity always cause that antagonistic behavior?
No. With shared negative conditioning, the teacher and student can represent the same negative target, and positive-only updates improve both branches together. The ambiguity becomes harmful when the teacher has extra information in its negative branch, as in reference condition distillation.
What does the proposed branch aware objective supervise instead?
The method is positive direction matching, or PDM. It has two terms. One matches the positive teacher and student predictions directly, and the other matches their CFG conditional directions, defined as positive prediction minus negative prediction. These terms prevent one branch from hiding an error in the other. The direction term is D equals V plus minus V minus. PDM therefore compares D from the teacher with D from the student, while also comparing their positive predictions. The first term anchors what is generated, the second anchors how the condition changes that prediction.
Why does the direction term matter for the student that lacks the teacher's extra negative information?
The student may not be able to reproduce the teacher's negative prediction itself, but it can still learn the teacher's conditional direction together with the positive prediction. This gives the optimizer a meaningful target for the change caused by conditioning, instead of asking the guided sum to absorb both errors. For dense to sparse video control, the paper also limits supervision to the first case student visited then assigned states. Full trajectory supervision would require a teacher call at every state, so this early horizon reduces the cost while retaining the states most useful for the distillation signal.
How did the experiments separate the benign case from the failure case?
They compare text rendering distillation, where positive and negative branches share the null text condition, with reference condition distillation, where the teacher retains a reference while the student does not. They track the positive and negative branch error norms during training for naive guided matching, positive-only matching, and PDM. The top row confirms the benign regime. All objectives reduce both errors together in text rendering. The bottom row exposes NBA. Naive and positive-only matching lower the positive error, but push the negative error upward, while PDM keeps the negative error nearly stable. This is the direct evidence for the paper's branch-level diagnosis. The main application is dense to frame video control with pose, depth, and scribble conditions. The baselines include the unadapted sparse control student, supervised fine-tuning on diffusion states, off-policy teacher matching, and naive on-policy matching.
At the training guidance scale, does PDM improve control itself, or only protect against the scale mismatch?
It improves control at the matched scale too. Across pose, depth, and scribble, PDM gives the most consistent control fidelity gains, while an alternative branch-aware baseline also beats naive matching on most metrics. That shows the benefit is not only a correction for testing at the wrong guidance scale. The guidance scale sweep makes the robustness difference clearer. Models are trained at scale 5 and tested at scales 1, 3, and 5. Naive OPD degrades sharply away from its training scale, especially at scale 1, whereas PDM and the branch-aware comparison remain much more stable.
What do the qualitative examples show that the metrics do not?
In the video examples, PDM keeps the person, seen on motion, closer to the reference across keyframes. Naive matching becomes blurry or loses the intended appearance at off-scale guidance. The reference-conditioned examples show the same pattern. PDM preserves the supplied style more consistently, while naive outputs drift and develop artifacts. Two ablations explain the practical defaults. The direction matching weight lambda equal to 1 gives the best overall control fidelity. Setting it to 0 reduces PDM to positive-only matching. For the supervision horizon, K equal to 8 gives the strongest control among the tested choices while costing far less than all 50 states.
What remains uncertain about the two branch array objectives?
The paper is careful about one limitation. PDM and the alternative branch array objective share the same zero loss solution under non-denier traits. So PDM's advantage is empirical rather than theoretically settled. The authors also leave extensions to other guidance mechanisms and other teacher-student conditioning gaps for future work.
What is the one-sentence takeaway?
Matching a classifier-free guided prediction can hide errors between its positive and negative branches. PDM makes those branches accountable by matching the positive prediction and the conditional direction separately, which suppresses negative branch asymmetry and produces more reliable dense to sparse video distillation across guidance scales. That wraps up this paper walkthrough.